Stanford University.
I just wanted to start by saying that I got interested in energy in the small because I do work in integrated circuits, and it became very clear to me about a decade ago or more that energy was going to be critical for us to build and continue to scale performance in information technology. What I thought I'd do in this for the panel is let's just first introduce the panelists, and I've asked the panelists just to each say a little bit about who they are, where they work, and just to give a sense about how they got involved into energy in one way or another. So I'll start off with my colleague, Balaji.
Thank you, Mark. I'm Balaji Prabhakar. I'm a faculty member in electrical engineering and computer science at Stanford. And my area of research actually is computer networks. So I do more of the sort of stuff that Cisco and Google and others do, data centers, internet algorithms. But about 2 years ago, I got stuck in traffic in Bangalore, which for those of you who've been there know how bad it is. And this was on my way to Infosys to have some sort of a technical meeting. And it was to do with computer security, unrelated to anything to do with what I have since been doing. And I thought, well, something should be done about this, something could be done. And then just conversations led us to actually having Infosys agree, or in fact they were keen, to run an experiment where we will pay their commuters, their 20,000 employees, pay them money to travel in off-peak time. Okay, so get rid of congestion. Now this has serious implications in the sense that you'll save a lot of fuel emissions in addition to all the headache that commuters face. Now that experiment ran for 6 months, and the company gave us enormous access to things like payroll systems and access to times of arrival, the badge swipe-in times. And it was all done very quickly and in short order, that is, and then it could be done, a 6-month experiment. There's a paper on this, but effectively, we actually managed to pay people and double the number of people coming early from about 4,000 to about 9,000. Okay, and so this led us to thinking, well, you have now slides, this is the academic way, and then we start talking about it. And then the Stanford folks, we have a problem of congestion, which may not be visible to you, but you look at any campus shuttle, you'll see there's reduced peak hour trips. And so I got into congestion, understanding congestion. And turns out there is all this, mode shifting is a big movement around the world. Get people out of their cars into the public transport system, saves a lot of gas. And then some numbers are staggering. In the US, in 2007, every year there's a number that's released by this Texas Transportation Institute. And it turned out that we wasted 3 billion gallons of gas by driving cars that were stuck in traffic, or by not driving them. Cars are stuck in traffic. How much gas are we wasting, idling? Okay, that's 3 billion gallons. That's equal to 6 days of gas consumed in all of the US. So I looked at this number and I thought, if you could take away 10% of this, that could be interesting. So I got involved in this. Then now there's a Stanford project that the US DOT has funded. Other projects like the Bonneville Power Administration up in the Pacific Northwest, with whom we've got a project through ARPA-E. Some colleagues of mine and I are involved. Incentives are just nicer, it seems. People like carrots. Nobody likes sticks.
Nobody likes taxes.
Right. So that's what I'm doing now, and I can see a lot of interplay between my computer networks interests and my societal networks interests, which is what I call this work.
I'm Paul DeMartini. I'm Chief Technology Officer and Vice President of Strategy for Cisco's smart grid efforts. Recently joined Cisco from Southern California Edison, where I ran the smart grid research, development, and demonstration activities, and involved in policy development, and have been in the energy industry actually my entire career, both from utility and on the competitive side of the business, including a short stint at an oil and gas company. My sort of move into looking at renewable, cleaner energy future and looking at a more modern grid started about 15 years ago when I left PG&E and got into the unregulated side of the business and started to look at, actually to start, I was doing a fair amount of consulting with City of San Francisco and the Hetch Hetchy project and how they were looking at expanding off their portfolio, the hydro project, into other renewable and cleaner resources within the City of San Francisco. towards looking ultimately at municipalization at that time. And obviously, it's a continuing theme that has been continuing over the last couple of decades. But over the last 10 years, I've been very involved both at Southern California Edison and prior to that, looking at taking technologies and applying both from the information technology side and advancing energy technologies, things like energy storage and the like, on how we can start to take these elements and put them together to create this more modern grid. And so that's been my focus.
My name is Pat House. I'm the co-founder and vice chairman of C3, an enterprise software company focused on bringing to market solutions to help monitor, mitigate, and monetize energy resources and emissions. And the way Tom Siebel, my business partner and co-founder of this company, and I got started is ironic. It was philanthropic. And we had been fortunate to be the co-founders of Siebel Systems, a company here in the Bay Area that grew to be significantly large and successful in scope. And after we merged it with Oracle, the company that we had both matriculated from, we found ourselves actively involved in a number of different philanthropic efforts, and we think we brought great solutions to bear to eradicate the demand for methamphetamine across this country. We did a lot in terms of sponsoring scholarship at Stanford and Berkeley and other universities across the country. And we started through our philanthropic efforts investigating what we could do to bring our successful resources to bear on innovating energy solutions across buildings. And we worked with a number of people in this room. We appreciate your help on that. We worked with Dr. Chu, in fact, on those efforts. And one night we were having dinner at Tom Siebel's house, and one of the people around the table said, really, we ought to start a company. If this is what we think is important over the course of the next several decades, is to help organizations of all kinds become more efficient in their use of energy by comprehensively monitoring and bringing to bear the resources to mitigate and then monetize those efforts for the point of financial competitiveness, then we should do the one thing we know how to do well, and that's bring software solutions to market at scale to handle the largest problems there are. So in 2007, we founded C3, and much like we have our other companies, we brought our 50 best friends together and took the money from them, took the expertise from our friends, and now have launched into the market with a very large endeavor in this space. So that's how we came to solve this problem.
Great. Bill?
I'm Bill Weil. I'm Green Energy Czar at Google. Have what I think is the best job in the world and certainly one of the most fun titles. I've been interested in renewable energy and energy technology pretty much my whole life, but actually followed a path through computer science. I've known Mark for, I don't know, a long time. Worked and talked with folks in the EECS department here at Stanford for many, many years. And about 5 years ago, 6 years ago now, decided I was ready for the next phase of my career and decided to see if I could actually do something about renewable energy and climate change professionally, not just in my personal life. And was lucky enough to land this gig at Google. I lead a group of people who are focused on renewable energy, energy efficiency, what we call energy information systems, systems designed to help people, not just businesses, but also consumers, understand and manage and ideally reduce their energy use. And then we have a lot of people around Google that we collaborate with, doing many related things that are intended to help both Google and the world manage and reduce their energy and also understand the impacts of climate change, things like deforestation and so on.
Great, great. So I just wanted to start with sort of a little opening. If you think about it, there's a lot of analogies that have been made between energy technology and information technology. And oftentimes it's said that they're separate, right? There's information technology, there's energy technology. But I think as you'll see, as you've already heard from the panelists, there's lots of applications for things that we might consider information technology in energy technology. So we have in information technology been able to build incredibly cheap and powerful computing systems, been able to create lots of different sensors, and develop incredible analytics, right? And all of these could have great play within the power industry. So I'm just curious in the panel, where do you think the really big synergies between information technology and energy are? And where do you think the biggest win's going to be, or where do you think the opportunities are? Clearly, Pat, you think it's in basically being able to optimize and manage some of the analytics, but I'm just curious if we go down. Let's start with you. So
It's a good question. I mean, I think about this, you know, the data that underlies this. And, you know, we think about in this 20, 30, 40 cents at C3. You know, in 20 years, the population will increase by 20%. In 30 years, it's expected that our energy globally, our energy use will increase by 30%. In 40 years, it's expected that the energy consumption in the US will increase by 40%. With all the technological breakthroughs we're going to bring on board in terms of new sources of energy and less corruptive conventional sources of energy, there's no way mathematically to solve that problem without becoming dramatically more efficient at what it is we do today with sources we know today. And the only way to do that is to inform ourselves with very large data sets about the precise use of energy today and the opportunities to bring products and services to bear to ameliorate that use of energy, and ideally do so with increasingly more clean sources, more reliable sources, less unpredictable sources. And the way to do that is to operate intelligently on very large data sets that come from very different sectors. So it's one thing to know your energy bill itself and the composition of that energy. It's another if you are Dow Chemical and working across 493 plants around the world to know down to the energy consuming asset with reliability, what is the consumption and how does that benchmark plant by plant, and how does that benchmark against the provider's recommended energy use according to those assets, and how do you profile against your competition? And to be able to use information technology, in this case large-scale software, to operate on diverse sets of data and calibrate that use across the various considerations that will help mitigate it. The incentives that are available from government and utilities to scientifically bring those information sets to bear and reduce that use of energy and then monetize the output of it, both in terms of the operational efficiencies it will bring in terms of the intensity across the products you bring to market, but as well as in your ability to bank and claim and hedge assets, and frankly, to be in a better position to be informed to do really good negotiations with your energy providers around the world in terms of having forward visibility and forecasting uncertainty. And this is a perfect use. If there are computer scientists in the room, you know that this is a perfect use of computer science to be able to take multiple variables and in a scientifically sound way predict uncertainty and forecast forward so as to make good operating decisions. And what's interesting now, I mean, we're seeing energy, which was somewhat ancillary to what a CEO thought of or a CFO had to reason with, become a core fundamental issue in terms of what they consider fiduciary and legal responsibility. And they are, for all intents and purposes around the world today, uninformed by good information systems that would provide a reliable platform around which they would make fundamental operating decisions. Where to source plants, what hours to run plants on, what materials to use, what products to ship and not ship, and which should be offshored and onshored. And without that information system, there's a blindness in some cases to what compromises 10 to 20% of the operating consideration of the company. So that's our job, is to bring robust information systems to bear to calculate the equations that inform the operating executives and their ecosystems, frankly, the entirety of the supply chain and the value chain which they sell through, to systematically characterize the use of energy and other valuable resources and the resultant emissions in those products and make good operating decisions.
Paul, do you want to, what do you think are the sort of the key opportunities here in that combination?
Well, obviously, as Pat said, I mean, managing that data, informing, and being able to make effective decisions about how to optimize the resources and the assets that are in place today and are going to be built is important. I think clearly in places like California and many parts of the United States where you have a system average load factor that's about 50% is a problem. You know, you wouldn't run an airline effectively at half full all year, only to have all the airplanes full on the Thanksgiving weekend. That's effectively how the electric systems run today. That's not an efficient use of that asset. Billions of dollars. I mean, EEI is estimating that over the next 20 years, Edison Electric Institute, which is the trade association for the investor-owned utilities in the United States and into North Canada, they're projecting $1 trillion of investments going to be needed in modernizing the grid, both replacing the basic infrastructure, much of which has been out for 40 or 50 years, as well as expanding the system to adapt to the growth in the United States. And so you have a lot of a lot of capital that's going to be expended and needs to be operated efficiently, that's for sure. What we look at Cisco is that all of this requires a communication network that needs to be put in place to be able to connect these sensing devices, these intelligent devices that are increasingly going to be part of this $1 trillion investment that is going out. When we talk about energy technology anymore, it means that there's also an element that is intelligent that's built in. It's very difficult today, whether we're talking about a smart meter or we're talking about a circuit breaker or we're talking about a transformer, these devices anymore are increasingly having sensing devices built in. There's some level of intelligence. There may even be some sense of analytics built in to be able to manage these devices, manage the grid more efficiently. They all need to be connected. Now, when we start to shift to the consumer side, whether it's the residential, the commercial, or the industrial, clearly there's been a proliferation of sensing devices that start to feed the data to the kind of analytics that were talked about. That connectivity is required to be able to scale at a massive level, not unlike what was done in the internet, and we're clearly seeing that in this space. And it is a need to be, as Pat said, for software, the same thing exists for networks. We need large-scale, proven network designs, modern networking technology and capabilities and architectures applied to these problems, because we're talking about tens of millions of connected points, just even for a utility like Southern California Edison. 5 million meters. Just 2 devices beyond that meter that need to connect starts to get you into some very large-scale problems that utilities today, even like a Southern California Edison, doesn't have any more than 50 or 100,000 devices connected. So to go from 50 or 100,000 devices to 10 or 15 million in the span of 10 years is a dramatic change in the way that they need to be thinking about building scale networks. And that's just one utility out of the 3,100 in the United States. So very large scale challenges. And when you start to look at the United States, that's just one place. This is a worldwide phenomenon when we talk about smarter grid modernizing. And it's very interesting to see what's going on in Australia, what's going on in Europe. Certainly in Latin America, Brazil is starting to really ramp up their efforts in this regard. Russia is starting to really focus on this, because in many places they're focusing on how do they integrate these renewable resources, both the larger scale resources as well as distributed, and addressing the modernization need. And so at the same time, as you make these investments, as I said, you start to build in the intelligence as you go along.
So Bill, Google is about analytics and basically serving large numbers of people. And I know that you've worked on some smart meter stuff yourself,
right,
and Google has been involved. So where do you think is the best intersection between information technology and energy, and what kinds of stuff has Google been doing already in this area?
Well, I come at it from a couple of different perspectives.
Sure.
I've been schizophrenic for a long time. First of all, this question of sort of where is the best synergy between the two areas, between the IT and the ET, if you will. The other one, and I think that in some ways drives us to doing the easy stuff, to be provocative.
It's always good to do easy stuff.
And to do the stuff that clearly we need to do and that we can start to do now and that will make a difference now, but that at some level won't get us to solving the hard problem, the real underlying problem. And I think Tom, I actually got some advice or heard someone give some advice recently about, if you want to give a talk or you want to be on a panel, actually the best thing to do is to follow someone who's really good, because people are all charged up, they're excited, they've said good things, you can kind of refer back to it. So to come back to some things Tom said, it's a good piece of advice to remember for those of you who haven't given many talks to. So Tom said a number of things that were, I thought, inspiring and really interesting. One was, ET really is different from IT in the sense that energy is a commodity. Not only is it a commodity, it's really cheap. So we can get people to use less. We can do that by putting a tax on it. We can do that by giving them technologies, as long as the technologies don't cost too much, that help them use less. Sometimes you can put that technology in front of them and they still won't use it, because the amount of money they'll save is below their pain threshold and they've got better things to do with their time. And we've seen this in some of the smart meter work we've done. Sometimes people will just be all over it, and sometimes like, you know, if I could save $10 or $20 a month, I don't care. You know, when I was talking about our power meter work up in the Pacific Northwest, a lot of people said, you know, the money savings are great if people can save a little money, but up here power is so cheap, that's not going to sell it to many people. And actually that's kind of true in most of this country. So that is a huge problem for getting at how we actually address climate change. So the easy stuff, I would argue, is actually the really hard problems of the analytics and the networks and building these, you know, this modern grid, not the 100-year-old thing we've been operating or still operating, but a modern grid with sensors and control mechanisms and the analytics and communication to sort of manage it all. That's actually a really hard problem. And building it so that it's secure and you know, robust against outages and against terrorist attacks and everything else you might imagine. That's not an easy thing at all. And for people here who are, you know, in computer science and looking for ways they can help in the energy sector, you should be all over that stuff. Integrating intermittent renewables is another really important hard problem. You can do that with storage, which is expensive. You can also do it in part with control mechanisms. Imagine if you could control the loads that are using all that energy to follow the renewables instead of today where basically the grid is managed by having the generation follow the load. What if we could actually just turn that on its head? Now you wouldn't want to do that with the lights because John Hennessy would say, hey, I want the lights on. But you could do that with your HVAC system if you had thermal storage. And in fact, people today are putting ice storage systems next to their mechanical chillers as retrofits and sometimes as new installations because it allows them to make the cold, make ice at night when rates are cheap, and then distribute the cold around the building during the day when it's needed. Once you do that, you can now say, well, let me turn that compressor on and off a few times an hour actually to dispatch the load to match the generation or to match whatever I need to manage the grid. But now you've got this massive control problem with, you know, around California, tens of millions of devices or hundreds of millions of devices you have to control. I don't know how to solve that problem today. I know how to do simulations that show it might be solvable, but I don't know how to solve it. So I think there are lots of opportunities there that the IT industry is charging at and is all over and had better be all over, and I think we can make a huge amount of progress on those in the next 5 years, 10 years. There are businesses to be built, there's money to be made. But then I come back to what Bill Gates said in his TED Talk, which is something that we've been sort of trying to preach for the last few years, and which Tom said, which is that we all need cheap, clean, reliable energy. And there are going to be 9+ billion people in the world in another 40 years. And they all want the level of prosperity we have. And if they do it with the kind of energy we use, we are probably all pretty well cooked. And certainly our children and grandchildren are cooked. So the question is, how do we provide all those people with energy? And even if we make the world more efficient and reduce our energy intensity by half, which I think would be an astounding thing to do over the next 40 years. And I think would use a lot of the technologies that Google and C3 and Cisco and other companies have. We'll still use more energy than we use today in the world, if many of those 9 billion people are more prosperous. So they need clean energy. Some of that is a mechanical engineering, electrical engineering, material science, physics, et cetera problem. Some of it is computer science and IT. For example, one of the companies we've invested in, eSolar, is building solar thermal power plants, and they're trying to take some of the hard problems that people put a lot of money into structures for heliostats that have to track the sun and keep it focused on a tower. They're trying to take some of the cost out of those structures and put it in software, which then you can just reuse. So that instead of having to calibrate every heliostat very carefully and go out and recalibrate and so on, they're doing that automatically. We're looking internally at Google at ways of doing that with closed loop tracking to take even more cost out of the heliostats. We're not sure yet if that'll work, but we think it might. So I think there are things like that that can be done to put IT in the energy generation to help make it cleaner. Same thing on the wind side. Wind farms today don't have very good predictive power for how much power they'll be generating in 5 minutes or 15 minutes or an hour. If they could predict better, then managing the grid would be easier, and they could actually sell their power for more, which would help that industry, and they could build more wind and so on. But that takes sensing of weather conditions locally and regionally. It takes better prediction of what's going to happen given the local topography and so on.
Yeah, and I agree completely in what you're saying. If you think about it, a lot of the growth in the IT industry wasn't to build computers per se, but rather to use computing in various ways to make other things easier or cheaper, right? So my favorite example is door locks, right? Nobody really wants a computer in your door lock. It's just done because it makes the cost and the capabilities of that system much better. And we could, in many of these generation facilities, think about ways that IT could make the plants more efficient, could basically make them cheaper to manufacture, higher energy outputs, and all these other factors, better predictors. So that's clearly a way that we can do things. Now, Balaji, your take on what the big opportunities are a little different, I think, from the other people over here, because you're more into trying to deal with the hard problem, which is how do you get people to actually do the right thing. So,
well, actually, I'm going to do what Bill said, borrow from Bill's main points. And there are two things that I think that align well. One is this hard versus easy. Let's start with the easy part. The sensing and networking technology, right? So my research area is computer networks, and that's the number one thing you learn is how to make things scalable. And after that, you worry about efficiency and so on. So there's this sort of list of properties that sometimes gets inverted from typical systems. But if you look at the internet revolution, there are some things that we've done as architectural principles, which I think we could do well to remind ourselves about. There's this idea of the end-to-end principle. They don't put the intelligence inside the network, because that'll just make the network so complicated that it'll crumble under its own weight. Put the intelligence at the edge, right? So if you look at the computer network, the internet, for example, the network relative to the end systems like our desktops and laptops and now iPhones and other gadgets are less, they're doing less. I mean, they're just dumb forwarding engines, roughly speaking. This is in contrast with the phone system where, you know, the phone is like really dumb relative to the network. And it's one of the things I've been seeing in the area of congestion charging. It seems like one of those things where you could use this. Most prominent examples of congestion charging are in Singapore and London and Stockholm, where the road system is sensing the vehicles. And so in Singapore is RFID system, which is less intense. In Stockholm and London it's video surveillance. So they look at your license plate numbers and then optically recognize. Optical character recognition tells them whose vehicle it is, and then they'll bill you. And if you were to think of it, you know, from this perspective of where should the intelligence be, it seems distributing the intelligence to vehicles is a good idea. And so the project we're doing at Stanford, we're taking the RFID route, but just passive RFID tags and stuff. But that's an example of an architectural principle. Then there's the other thing which we learned in the internet era, building a network or getting people to adopt something. Just say best effort, right? Don't promise anything. Starts with nothing. Just say, let's start and see this thing that Friedman was saying, convince Hennessy to buy 10 handphones and then slowly do this, and then it'll scale at some point and it'll monetize itself and find purpose. This is something we've seen just 10 years ago, right? All this irrational exuberance that technologists and mostly consumers got blamed for is actually what's the internet revolution, right? It starts with nothing, and people just imagine things, but there's some APIs that are built for you and me to hook into, right? Like selling socks on the internet is made possible by technology, right? But now people start imagining things. I think that's something we should, again, pay close attention to. I look at these road systems or grids and stuff, and what I feel as a researcher is that we don't have the right hooks. We don't know where to plug into this. You know, how do you just ask the question, what if I change the generation or distribution in this way? It's not easy. So we have to build all the simulators now, and there, you know, there's folks here, Amit, who's doing this, and we're getting there, right? So this is sort of the, how do you build, you know, things, models, and, you know, mental models even, and to grasp the significance of the work you're doing. Then there's the other thing, the hard part. Something that Bill said is absolutely right. This is something I'm noticing just for the past 2 years, which is the amount of effort required to do one of these good deeds is completely huge, or insurmountably large compared to the payoff. Okay, it's just the disproportionate amount of work you have to do to get money from returning recyclables is just not paid off by the effort. I mean, the value of it is just 5 cents, right? So if you take congestion, which I alluded to earlier, it cost the U.S. in total it was $87 billion in 2007, the cost of time and fuel. How much time did people waste on the road stuck in traffic? How much gas did they burn while they were stuck in traffic? Just that. Add that up across the U.S., and the number was $87 billion, okay? Across 435 regions measured by this Texas Transportation Institute. Now, you look at the number and you say, well, what does it mean at an individual level, okay, per day? And it's less than $1 a person per day, okay? Now, if we
the pain for those people is not the money they spend on gas, it's the time they wasted in traffic.
That's the most noticeable.
Right.
So this brings me to another paradoxical thing I observed. So, I was in India for a conference in August, and the lights went out. Immediately, the hotel's generators took over. So there's a lot of brownouts that take place. And the most interesting thing I observed was there's road congestion, and there's congestion on the grid. Road congestion, nobody blames the road system. They might blame it for not being wide enough or signals not being, but not, you're in traffic jam, you just look around and you're blaming all these people around you, right? They're the reason why there's traffic, you're stuck, not you. You have nothing to do with this, right? It's the perfect crime. Nobody's a perpetrator, right? Everybody's a victim. Look at grids, power goes out, nobody says, is all the other ACs around me? Nobody says this. They don't see these ACs. Right, so there's this particular way in which human beings seem to absorb and understand these events. And now, so the way we went about trying to make it matter to people is, so if the amount of return for the deed you perform is too small and too insignificant, you may not perform it, right? And how do you now make it matter? So the way we did this in the Infosys project, and we've carried on with it since then and refined the idea, is to pay with raffles, right? So lotteries serve a purpose precisely in this case, okay? And I'm not saying pay a huge jackpot to the one person who helped you decongest or turned off a light bulb. That's not the right idea. The right idea is to pay these so-called micro lotteries, right? Like $10, $25, but as a lottery, okay? Because at an individual level, if you were to go around rewarding everybody, you may have nothing more than 25 cents or $1, okay, to pay. But if you made it like $100 or $200 and just so, that is random small micropayments, okay, then it might make a difference. And that's what we found in the Indian experiment. And we've carried that on a bit, okay. And so to summarize, now the way I see it is, as an IT person, there are 3 kinds of networks we human beings seem to interact with, okay. There are the classical physical resource type networks like transportation systems and energy systems, waste management systems. These are all networks. They've arrived in human history at different points in time. And the most recent arrivals are these sort of communication networks. And communication networks seemingly have this capability to just have fatter and fatter pipes. They're not somehow same constraints, don't apply to them as physical networks seem to have. This is a big deal, right? So you have those networks. That's happened in the last 50 years. And then the new networks are the social networks, like stuff we do when we, Twitter, Facebook. So it seems to me that the interfaces have been built between the physical networks and this computer network, and that's sort of what Paul and Bill and everybody's talking about, right? This is the smartening. When we say smart grids, smart roads, and so on, that's what we mean with embedding stuff with sensors, networking the sensors, gathering the data, allowing these networks to control themselves. That's what's smart about them. That interface has been built. And of course, social networks and communication networks have a built-in, bond at birth. What I think is really exciting, and that's what we focused on, is to get this social networking that we all do. So we all get stuck in traffic or something for an hour a day, let's say, or we make commuting trips for an hour a day. That's physical world movements. And I don't even know who the other guys are on the road. They're not my friends, they're not my acquaintances, they're just strangers. Okay, but they matter to me in a way that's actually more fundamental. Then what do? Then I go home perhaps in the evening and do all the social networking stuff, right? These are my friends. What we're focused on is trying to make these two meet, okay? I think there's an interesting interface to build over there and make it matter, give rewards out through social structures, right? Do a friends and family for energy savings, okay? Find ways in which you can just pay out through the sort of social structures that everybody's familiar with, right? So you saved some fuel and I get cell phone minutes, okay? Because that's who's giving you the rewards, okay? So that's an example. Okay? That's what we're trying to do.
Great, great. So one of the things in all these different opportunities from the short term, basically merging of information technology with the basic energy technology, to I think the longer term vision of basically fundamentally changing some of the processes we knew to create new energy that use really very strong IT controls. If I was thinking of being excited about this area, because I hear a rumor that there's lots of jobs going to be available in this space moving forward, right? What are the kinds of skill sets that you would think that would be necessary if I'm a student here or someplace else? What are the kinds of things that would really be useful to know to be successful in this field?
I think a really solid grounding across computer science. And not just, that's not programming, that's systems, that's distributed systems, communication, network protocols, and what I would really think of as control systems. Because what we're talking about with whether it's a communications network or the electrical grid or whatever, it's a control system. But then more broadly, when I think about the stuff we're doing with Google Power Meter and the ways we've thought about how do you motivate people to make changes that might not matter that much to them other than maybe saving them a little money or a little bit of gasoline, which is money, is people who can think about those issues from a sociological or behavioral psychology perspective and understand what's been done, what works, how to study what works, that kind of thing. And then, for the underlying generation problems, clearly mechanical, electrical, engineering, all of that kind of stuff is vital, material science and so on.
And I would say if you think about this, I don't think this is a problem that can be disaggregated, and I think that's a lot of where today's challenges come from. An individual operational manager has responsibility for the energy used in a singular building or a facility or a business, and until you look at the overall system that underlies it, you can't get to the well-informed solution. So I think those of you who are studying in this area have got to see this as a system. These are the largest data problems that exist in the world. If you think about time sequence data from millions of points of individual pieces of equipment that then have to be brought to bear in some kind of intelligent executive synthesis that can be brought to an operating team to make decisions, that is a really fascinating challenge. Take time sequence data that can be analyzed and from which intelligence can be gleaned and show that in an executive dashboard that is decisionable, and then do exactly the inverse at the same time. Reduce that data down to the individual employee or citizen or student level in terms of how they contribute and can see metering and monitoring and feedback systems about their own performance and the way in which that is contributing. And don't think about it as a singular information system. Think about it as all the energy sources that provide this, all of the assets that consume it, all of the financial incentives that can be brought to bear, all of the legislation that mandates it, and the performance plans, the financial performance plans of each of the individuals who contribute to that. That is a massive data information problem that has really interesting human interface characteristics, as well as the optimization engines that work underneath it that are really hard computer science. It has really interesting information presentation challenges in terms of how you inform and enable people to take immediate decisions on real-time data that is complex to get to. So I think those of you who work on the human factors end and care a lot about that and care about individual performance characteristics based on real-time monitoring systems, and those of you who want to work on Hadoop and Cassandra and other very large data problems and optimization engines for predictive analytics and analytics that have to be derived from partial data have really meaty computer science challenge opportunities. Okay. And we'd like to talk to you afterward.
Well, I certainly echo what was said by both Pat and Bill. I mean, those are exactly areas that are of focus and need urgently, actually. I think the other thing that I would sort of build on what Pat said and say that if you've looked at systems engineering, it's an area that really helps to start taking the big picture and start to organize it in a way about how you start to implement these systems. Most of the industry worldwide is starting to really use systems engineering as a way to try and tackle these problems. And architecture today is one of the biggest areas of need in terms of understanding effectively how to create the urban blueprint, if you will, for what this grid looks like. You know, as we talked about, there's going to be a different configuration to this network as we go forward, particularly in the distribution system. The distribution system was designed for a one-way flow, not unlike the water system. And that's not going to suffice in a world in which we have distributed resources, very pervasive distributed resources, with not just two-way power flow, but n-way power flow. So a completely different architecture or design for that system is going to be required. And then, of course, the overlay of all the protection and control systems and feedback loops and the like. So a lot of opportunity still to be very focused and involved in there. And then again, to build on Pat's point, this convergence of technology, policy, and economics is really at the heart of a lot of debates today about how to move forward with investments, that $1 trillion in the US, worldwide, you know, significantly greater. All of that comes in many cases in front of regulatory commissions, some legislative involvement on those issues, and trying to really understand how to put forward the best set of programs. There's a big trend right now, you've probably seen in California and other places, where states or countries are requiring deployment roadmaps. Those deployment roadmaps really come at the nexus of this trade-off between the policy, the economics, and the technology, and understanding those other two dimensions in addition to the technology are really helpful in that dialogue.
Okay, so one of the issues that people have been discussing is that information technology is great and we use it every day, and if it goes oops, computers crash or networks go down, or there's denial of service attacks or something like that. That's a little scarier if it's basically distributing real power, because if you oops on a power, things go boom a little bit more than computers. So I was just wondering how much of the sort of stochastic nature of the whole problem and what kind of reliability and security stuff have people been working on or thinking about, or what work needs to be done in that area to really make this stuff effective, right? Because the first time something goes boom, it's going to set the whole industry back probably a number of years if it happens. Anybody want to?
Well, I think just to pick up on the one point you said, which is it shouldn't be taken for granted that this is a stochastic world. It's going to be. It's emerging right now. But it's important to understand that the utility industry today is operated on the deterministic model. Load, for all intents and purposes in the aggregate, is very predictable based on temperature and weather conditions and the like. And so it's essentially treated as deterministic. Generation resources are largely deterministic today. That's not going to be the case, and it's already happening that we have to shift to a much more stochastic model in terms of how the whole systems operate, from planning through how the systems are implemented, designed and implemented, and then it's operated. And that's a fundamental shift that's going to be required. Now, so building on top of that, dealing with uncertainty and the risk that are inherent with that sort of system. And again, this is a system that was not unlike an old airplane, propeller plane that was inherently stable. Now we're moving to a fly-by-wire type system is what we're talking about. So in that world that Mark's talking about, sure, any element that starts to disrupt that can have ripple effects that can be catastrophic. So again, these issues that we've talked about in terms of how to think now about how to make sure we build those into the system today these are being deployed is really the essential thing. We're not going to be able to retrofit. This is not a system that recycles or has a life cycle of every 24 months like we do with other technologies that we've been used to in IT, or 5 years or 7 years like software at the enterprise level. These are 15, 20 year, in some cases 30 or 40 year assets, and so it's important to get it right from the beginning. It's much like building an airplane. You don't build an airplane and then try and fix the bugs once it's up in the air. You're going to have to get it right from
the
outset.
Well, you shouldn't.
Yeah. Yeah. So this is a different approach to trying to build these systems out.
And it's, if I may, it's not just energy. I mean, if we really think about this, we're talking about resources.
Right.
We're talking about the limitation and the strategic nature of resources. And as hard as we have to think about energy, we equally have to think, if not even more urgently, about water. You talk about a precious commodity that is going to limit where people and how people live and how organizations run. And it's very hard to differentiate energy from water. It's very hard to separate these resources. And another one, we've recently seen this announcement about, rare earth metals, or rare earth materials, right? And talk to the people at Boeing about this. Talk to the people at Boeing who deliver aircraft to the United States government, and talk about the implications across the 4 million parts that make up an aircraft and how many of those are dependent on those metals, and what implication that has through the supply chain of Boeing as they plan forward to deliver on their contracts to the US government. Very, very significant. So someone mentioned, I think Bill, it might have been you earlier, material sciences. I think one of the most creative breakthroughs we're likely to see is a substitution in the way we have confined ourselves to think about the way things are built today and the way things are transported. And you can't limit it to energy alone. You've got to think about water, and you've got to think about other constrained resources in terms of innovating a whole system. And I think you're right about this notion of architecture. You've got to think in large-scale terms about architecting systems that have interdependencies that we have not created interdependencies and we've not observed the interdependencies that have existed, and we've been blind to that. And now is the time to maybe do some cross-discipline work in terms of how your engineering groups work together.
Yeah, and I think in terms of getting back to the question of the electrical grid, I mean, I agree, water is a huge issue, other resources, and if we don't address that, there are a lot of areas that are going to be in big, I would say, in deep water, but they won't. But for the electrical grid, for example, as we build this smarter grid and so on, that's two-way or n-way, with much more complicated sensing and control mechanisms, I think we need to think very hard before we put standards in place and define exactly how it's going to operate about how to make sure that it is robust and doesn't go boom. And my sense, not being deeply immersed in it, but my sense is we haven't thought hard about that enough yet. And there's actually is a lot of room for cross-disciplinary work there, getting people with experience in the networking business, from Cisco and Stanford and other places, involved with folks from EPRI and the power industry to work on that stuff. I think that there are a lot of interesting challenges there.
Just to add to this, there's something which I find a little interesting in a technical sense and paradoxical even, is that when we try to build these sort of grids and road systems and water systems and everything, because the physical resources, it seems like we want to be really, really, really efficient. The one thing we know, say from building large scalable networks, is the more and more you make something efficient, the less and less robust it is. It's just a fundamental trade-off. Okay? The meaning of robust means you must operate under unknown input conditions. Mm-hmm. A necessity for building an efficient system, pretty much, is you know the inputs really well. Okay? And so you look at the way we went around building the internet, there's like lots of stuff that doesn't actually work. But the whole thing works, there are parts that are not working well, but the whole thing works well, right? There's building this reliable organisms from unreliable components. That's sort of what underlies the way we went about the internet thing. Here, it's just suddenly all the stakes are so high, because how can we just like waste water? We can't. But then we have to be nevertheless robust. It's non-trivial. There's another thing
So the issue is how little can you end up wasting and still be robust?
It's a beautiful curve, right? There's a robustness on the y-axis, and you want to be somewhere
and
here.
can you make it go like this, not like this? Right.
So there is that aspect. There's something else too that we've done in building these distributed systems. One of the things that we've done there is like the essence of a distributed system, is my way of saying it at least, is that there are all these components that are trying to work the system without knowing how big the system is even. When you're on the internet, you have no idea how big, who else is out there. You don't know who's going to share your bandwidth. So what you do, you don't know how much bandwidth you have, okay? So built into this whole thing is, I'm actually going to keep sending more and more data until a packet drops. When that happens, I'll cut my sending rate and then probe again. This is exactly how this so-called TCP algorithm works. So we build in this waste, namely drop a packet and retransmit it when it's dropped, okay? Just so we may discover the system we're in. That's the way you build this sort of distributed systems where you don't have to now put all this intelligence in one place and then worry about it, okay? Now, I look at that idea and then, you go to transportation networks. It's
You drive as fast as you can until you hit the guy in front of you. You back off.
That's right. Yeah, but if you think about the whole thing in the IT space, it's always been, how do I move something that was over here in the physical space that consumed real resources into the information space where the resources get cheaper every year? So one could think about doing the congestion kinds of back off, but you're not doing it with real energy flow. You're doing it in pricing systems that run on top of the energy flows, and you're basically bidding in the IT space, right? So where you have excess bandwidth because the bits are so small and they're getting smaller every year, instead of the kilowatt hours, which are big and they get smaller.
Actually, what you just said, there's sort of what I think is an interesting question I'd like to sort of throw out there, which is you raised the issue of pricing systems and price signals, and I'd like to encourage people to think of other kinds of signals or control signals, if you will, and control system structures than just ones based on putting a price signal out there. To some extent, I think the sort of free market ideology that's pervaded this country and maybe the world over the last 20 years or more has also
limiting.
It's permeated the way we think about systems.
Yeah.
So the way we should influence the way people use energy is by sending price signals. Well, that is one way to send a control signal and to have an impact. It may or may not actually have the end result you want. There may be other ways to design the system where price is one signal, but there may be other signals that are interesting to send that give you much better and more useful control over how, when energy is consumed and how much is consumed. But if the only mechanism you build in, for example, to your smart meter network is that the utility can send a price signal and that gets sent to appliances, that's the only control mechanism you've got. So I think one of the things that academics could study is what other options do we have?
Yeah.
And how much better might they work?
Right. What's the vector of things that you might want to communicate instead of just lumping it all into one?
Right.
Yeah. So we can talk a little bit more on the panel, but I'd like to open it up right now to questions from the audience. If you have questions about IT in the energy space that you're interested in, that you would like to ask any of the panelists, please feel free to stand up, raise your hand. Yeah. John Massey?
What's interesting is that a lot of the issues that you're talking about are ones we went through in a previous incarnation. And in particular, the reliability issue, we spent a lot of money to make sure the phone system would never go down, and it's expensive. Right? Now, the question is, there's the expense. Also, the issue that we tended to face that we sort of don't in the computer business is the longevity. Right? I mean, we worried about things that had to last 40 years. Right? So I'm curious if you're thinking about the issues of how you roll things out, knowing that there's a huge embedded infrastructure that has to stay and work together for a long time, and the expense of actually getting that last little bit of reliability.
Well, I think, as the point was made, there is this paradox about getting more efficient and optimization that also creates some instability or inherent instability in the system. And so, yes, that's a real issue. And there are a couple of examples I can share that are not just optimizing what you use, but also the changes in energy policy with respect to and climate policy that are affecting California potentially in terms of how the grid could be managed, requiring a new way of thinking about managing. For example, there was a policy that was initiated to not allow once-through cooling on the coastal power plants, that is, not cycling the water through once and then putting it back out at a higher temperature, which has an adverse effect on the ecosystem in the ocean and the waterways. But that could affect, say, in the Los Angeles area, about 9,000 megawatts of generation that's in the basin supporting that system. Those units provide something called inertia, reciprocal mass, to keep the system stable. The other generation that's available that is expanding is obviously wind and solar farther away, but you have long transmission lines, and so the system, if those plants were to shut down and we didn't do anything in between to mitigate that, that inherent instability, the lack of inertia, you could have a very unstable system there in the LA basin. The same thing could happen up here in the Bay Area with the plants up in Contra Costa and Pittsburgh and the like, potentially shutting down as well. The issue isn't should you do that or not, it's just that you need to take that into account and think about what those systems need to be. Now, the other part of your question is, yes, this is why architecture is very important, because one of the things that I think increasingly people started to understand is that you shouldn't be tightly coupling fast cycle technologies with slow cycle technologies. A circuit breaker, a power circuit breaker is a slow cycle technology. You don't want to tightly couple something that's going to be, communication technology that may be evolving every 24 months. And so this is part of actually some of the discussions that were going on around the smart meter systems, because you do have to put a communication module in that meter, and you're not going to touch that meter for at least 15 to 20 years, because the expression in the industry was you touched the meter, you paid for it if you had to go back out there just because of the truck roll cost and all that. So yeah, you do have to think about that. And one of the, although you all would take it for granted that people would think to do this, this was like a big breakthrough 4 years ago, was the idea that you'd actually have, use more modern computing, actually modern, it was computing from 15, 20 years ago. You'd actually create a software layer so that you have firmware upgrades that you could do over the air. Systems 3 years ago were actually hardwired. I mean, the firmware was burned in and you could never change it, and so you could never upgrade. There was no security built in. You could never upgrade what was there from a security patch or any of that stuff we take for granted. And this is the evolution that we're going through. Just to give you a sense of it, the utility industry, if you've seen that chart that Kurzweil put together that showed Moore's Law and backcasted it to the 1900, and if you've seen that, it's on Wikipedia if you'd look at it, just look at that curve and you can plot almost 10 years after the introduction of whether it was an electromechanical relay all the way through vacuum tubes, all the way up that curve. You can lag 10 years from that, and that's when the utility industry adopted that technology. Okay, so this is the dynamic we're dealing in. Is we're still in this, in this industry that we're talking about, trying to evolve very quickly. At the same time, we're moving very fast with these policies to push even more stochastic and dynamic operations onto this grid. So we're having to play catch up very quickly, which is why the demand for all the things we're talking about here.
And some of this is happening in some sense outside the utility industry. So there are companies that act as demand aggregators.
That's right.
And basically they'll take a demand response signal from the utility and then they'll tell all of their customers or their clients, I need a quarter of a megawatt from you and 100 kilowatts from you and so on, and those folks will shut down, reduce their load. And then the demand aggregator gets paid for that demand response and they share some of the money with their clients. But they're not regulated, right? They're basically bidding into the market, and they can iterate and they can evolve and innovate much faster than the utilities can. But it also means that they can screw things up much faster than the utilities. And so I do think, there is a reliability issue. You're right that AT&T, with the 5ESS and earlier systems and so on, enormous amounts of effort and enormous amounts of money went into making those systems very, very reliable. One of the things I think we've learned in the internet and with computers is that you can get reliability for a system out of very unreliable components. So you don't have to spend a lot of money on each individual thing. You can get redundancy in the system as a whole. I think the question is, how do we do that for the electrical system in a way that makes it stable? Because it's got, if you lose a packet, oh well, you retransmit. If you get a cascading effect in the electrical grid and the Northeast goes down, that's a bigger problem.
So there's one other thing just to add to this, which is test beds. In most of the other networking world, even wireless now, we have nice, real looking test beds. Okay. I have no idea how to think of test beds for road systems. I mean, in other words, academics like access, faculty, students, everybody likes access to take your algorithms or your protocols and go try it somewhere, right? This whole thing is essential. And this is a huge, been a problem. And so in some cases where we're able to get access to things and try our experiments, we call that a test bed. But to get something at scale is actually non-trivial.
Well, I thought we were all going to be part of your test bed for the
That's
parking.
right. Yes.
Okay, other questions? Yes, right here.
So actually, just a couple of comments first, and then certainly like.
I hope there's a question someplace. So.
Yeah. So first is about the complexity. You know, I think the IT industry gets really excited when we talk about millions of these nodes and how do you communicate. It seems to me that the outside the IT industry, people deals with complexity in a very different way. You know, particularly in the power industry, people try to simplify the problem instead of just deal with the complexity by building more, faster algorithm computers and networks. Aggregation, for example, Mr. Well mentioned the aggregation. I think that's a great approach, and that's a way to simplify the complexity, and also making the controls autonomous. So you gather information and use that locally instead of sending 100 miles away and expect something to come back. So I think that would be interesting aspect to look into from the IT perspective. Second is related to the cost. We talk about if I save $10-20 a month, I wouldn't care. And there might be a few people who cares, but in reality, he doesn't care. Most people don't care. But I think if we look at the price chain, there probably be a lot of other aspects you can quantify in terms of cost. I suppose Google must have a secret formula internally which tells you if I improve the power supply efficiency by 1%, how much money I save every year. I mean,
Seems likely.
I know you guys have that, but
Yeah.
a couple of months ago, I put in a proposal for New York State. By the way, I come from RPI, in New York, and it's about smart grid. And the proposal or the program requires 50% cost share. For those who knows the New York State NYSERDA program, it requires 50% cost share. And we're proposing $2 million project. So I was scratching my head. How do I convince university to commit $2 million into this proposal? It's always a challenge. But it turned out when I dig into the system we have, what we proposed was a campus-wide smart grid demonstration. So when I dig into the system, I learned that RPI is in the kind of process of preparing for $30 million investment in the power system because we are approaching the limit of the existing substation transformer. So the utility company has asked us to go to 115 kilovolt substation from the existing 34.5 kilovolt station. So once I made the point to the vice president of operation, I said, we do these, we could avoid or defer that $30+ million investment. He signed the commitment letter on the spot. So just a couple of comments. I'd like to hear the panel's respond on.
Well, just on your last point, there are two things that people are starting to look at pretty carefully. One is kind of a variation on voltage, and that is using voltage control at the lower limit of what's allowable on the distribution system to be able to get voltage conservation effect. And the estimates that EPRI and the utilities have been testing at Southern California Edison in the 90s, they had done the analysis, and it suggested that you could get about a 3% savings in energy across the whole system if you had a system-wide deployed volt-VAR control system. These same technologies, by the way, are going to be needed to manage voltage and VAR flow on distribution with wide-scale distributed generation. So you get two benefits, but 3% is a substantial number. The other is in the analysis that I was involved in, again at SCE on the smart meter program, we were the first to put in energy conservation benefits in a business case at a regulatory commission, and we estimated over the 20-year life that we could get effectively, and this was a very conservative number, the numbers can be as high as 5%, we used 1% voltage energy conservation effect as a result of the feedback from the near real-time energy information off the meter, that 1%, again a conservative number, was worth $164 million in net present value. So a big number, and 5 times that obviously is very significant dollars. And these are the things I think people are starting to look at is, both from a customer standpoint, how do we get at that value, right? That 164 million in the low case, or the 3% that you could get just by managing the electric grid, just by managing the voltage more effectively. And so those can be some big numbers while we're trying to solve some of these broader engagement issues on demand response and the like.
That's my point. Well-informed decisions in the short term will fund the more strategic, long-term, innovative, very costly research that has to take place to make step changes that are dramatically different. I wouldn't underestimate, the International Energy Agency recommends that, or suggests that 33% of the energy problem today can be cured through existing technologies and energy efficiency techniques that don't involve any new innovation. They involve a lot of aggregation of existing data and systems coming together and information to be brought to bear to determine how to make good operating decisions. But 33% of a big problem is a big part of the solution. In the short term, as we give ourselves time simultaneously to be iterating on the research and fund that research, frankly. And if there's one thing I think the university can help do that is really hard to do, and that's create policy alignment. Tom talked about, there's sort of absolute alignment in China. And that may not be the way we want to go about achieving it here or across other countries. But policy alignment is really kind of important, because policy alignment not only creates the governing structures, it creates the resulting financial incentive structures. And you look at the amount of incentive money that is being released to help affect these changes. Right now, it is neither tied back to a measurement system that is conclusive about the impact it had, nor to the legislation. And once you get those 3 things aligned, and that's where I think universities could help do an enormous amount of the study required to inform policymakers about how to do that. But I'm telling you, you get those 3 focal points aligned, where you've got policy and you've got incentives and you've got the information systems to drive it, we would solve an enormous amount of the problem today. And importantly, we would give ourselves visibility into what the longer term solution would be, and we would do it much, much more effectively in the medium and short term.
Okay, so let's get the microphone over to you to ask a question. In the meantime, so the question is, how can IT help do that policy alignment, right? So policy alignment is a complicated problem because it basically has a lot of stakeholders all over, and you've got to get them aligned. Known difficult problem. Is there stuff that, as IT people, that we could bring to bear to help this problem? Any ideas?
Well, for example, look today in the EU, right? Mm-hmm. Where there has been a scheme in place for a while, and look at the projects that have started, and look at the failure rates of those projects that have started that are available to claim credits back from the EU, right? There's a trading scheme in place. There are allowances in place. You can do offset projects to reclaim the investment in those. The failure rate has been astronomical. These things get overturned when it is time to claim them. And why? None of us would allow a project to run with no visibility, no metric system, no real-time monitoring, no auditability, and then come to the end and have a third-party verifier audit the results at the end of a project, after the investment, after the government monies have been allocated, and then overturn it. Absolutely unthinkable. And the easiest problem possible for information technology in the form of software to solve today. That's just common sense. That's just the instantiation of software early in the process, not as a terminal end of the process. And if we haven't lived through the quality control lesson well enough to understand, it changes industries permanently, right? Statistical process control applied to manufacturing really did kind of leapfrog Mill Standard 105D and batch sampling. And there were organizations and industries that understood that faster than others, and the auto industry moved, and the consumer electronics industry moved, and were governed by lower economics at scale as a result of those industries being brought to bear. not to deal with the products, but to deal with the process
Right.
through information that became a control mechanism through statistical process control. There is no difference whatsoever in measuring where these mitigation projects are today in terms of their impact to be measured and monitored effectively and auditable so that governments have the visibility and to know what to fund.
So I think, just to add quickly here, this is a big problem. The California Public Utility Commission, in their recent decision in the smart grid proceeding, put forward 82 metrics to measure progress towards a smarter grid. 82 metrics. Do we really need 82 metrics to figure out whether we're making progress? So I think, to Pat's point, if we could bring sort of a process view, an end-to-end process view to this, and start to look at what are the key areas that you're trying to measure towards the outcome of that process, I think we could probably simplify things quite a bit and really get more meaningful metrics towards progress that we want to see in California.
And I would say that's actually something that's true across all of government, not just policy related to energy and climate, but more transparency, more visibility into everything that's going on and into how effective various programs are. Not just, hey, great, vote for me because I passed these 3 bills or sponsored these bills, but rather this is what actually happened after those bills passed. Yes, we passed them, we never appropriated the money, nothing happened, or we appropriated the money and here's what happened. More visibility would help. I've got to say, Tom described himself as an optimist. I feel that I'm an optimist on this stuff. I wouldn't be able to work on it every day if I weren't. But these days, particularly the last year or so, I've become more of a terrified optimist in that I really worry we won't get the policy alignment, that we can't get, at least in this country, the government to do what we need to do. And that somehow, I don't know that IT, other than trying to shine a spotlight through transparency on stuff, can make a difference there. I think that just individuals can.
Advocacy.
Advocacy, individual and group.
Okay, please.
So I have a quick question about kind of effectively integrating renewables and demand response or smart grid. There's been a couple reports that have stated that it's the most carbon benefit or the most amount of carbon that's abated by utilizing smart grid to effectively integrate renewables, like the EPRI smart grid, green grid report rather, and the PNNL smart grid report. And I was wondering, it seems like this is going to dramatically increase the frequency of demand response, but maybe on smaller timescales, like say the spinning reserve or regulation timescale, which of course increases the complexity of the networking problem. A couple questions, I guess, are how do you think that this affects consumer response? Because, as a libertarian society, so to speak, it's very challenging to impose any form of kind of direct load control on people. So you're then talking about dynamic pricing, which is maybe more in the unit commitment timescale and not necessarily in the spinning reserve or regulation timescale. So that's one problem I see. But then also the latency of the network also becomes a problem within those finer timescales. So I was just wondering on your thoughts on those questions.
Sorry.
Well, I think, just real quickly, I was at the EPRI meeting 2 weeks ago, and Terry Boston, the CEO of the PJM market, Pennsylvania, Jersey, Maryland, the largest energy market in the world, and they have a very large demand response program. What he was talking about was, as a result of renewable integration and the ability to use demand response for ancillary services, that actually the time window that was going to be needed was actually expanding beyond the 4 hours that we typically think about in the industry to needing to have 6 hours of a window to be able to use to deal with the ramping of the renewable resources during the ramp up and ramp down periods. So actually having longer periods at which you need to have those resources available. And yes, maybe trying to figure out cycling programs that you can overlay, and so any individual isn't necessarily being impacted for too long. But this is causing, potentially creating quite a different dynamic than traditionally what people have been used to for example, residential customers with AC cycling programs or industrial or commercials that haven't been part of one of the aggregator programs. And so yes, there is going to be a fair amount of change there that's going to have to be reflected in a different paradigm for the program. We don't know yet what's going to happen in California, for example, when the existing AC cycling programs that are in place, which is fairly significant, is almost 400 or 500 megawatts air conditioning cycling programs that were based on reliability. The California ISO has already told the utilities they're not going to pay for reliability anymore. It'll be based on economics. And so as a result, there's a shift. All three utilities in the state are moving to pay for performance programs, as opposed to you get $200 for the summer to participate and we may call you up to 15 times. When you go to economics, it looks like a zero marginal cost resource. You will be called 15 times. That's a different dynamic, right? And so, yeah, so it's a really good point.
So I actually think that this is actually what we're really looking at through these experiments. I don't think price is the signal, because it sort of ends up being this 10-15%. If you want to shift demand from peak to off-peak, and you have 10% or 15% more cost for consumption and demand and, at peak time, and then less by that percent in the off-peak time, that's not enough. There's not enough you're going to shed. So one of the things we're trying to do is actually say, I want to pay a factor of 200 more. Okay, clearly I can't pay that to everybody, so I only want to pay to some 5 or 10%. But which 5 or 10% am I going to pay to? Okay, so let's assume some people are shifted load, and that gives them some credits or points, and then these are redeemed in this sort of raffle-like mechanism I alluded to, which is the thing we've tried. Now, the nice thing about congestion or demand, any kind, transportation, any network, computer networks, electricity networks, whatever, it really is just taking out 10% of the load. You don't have to shift the entire load. You should not shift the entire load, right? It's the last 5 or 10% that tips things from uncongested to congested. So simple things like, offer something to a bunch of people. 20% of the people that offered, don't go now, go half an hour later. Okay, you haven't left home. We can tell because we have all this fancy measurement equipment, right? And I'm not sort of, privacy is an issue I'll take on later.
Privacy and security, those are big issues.
Issues, and I will take. We're technologists. We know where you not do that, right? But just go half an hour later. Cross the Bay Bridge half an hour later today, and you have a shot at $50. Okay, I think that's the sort of factors matter, and that's what we're trying to do. Changing it by 50 cents or $1, I don't think it's having that big effect.
So
yeah, there are a lot of interesting, I think that's a really good model, and I think that there are other models people have been experimenting with out there. There's a company called Recycle Bank that actually contracts with municipalities to help them increase their recycling rate. And it does this by giving people rewards points based on how much they recycle. And then you can redeem your points for discounts at all sorts of places that basically want to participate in this program. And they use it for advertising to associate themselves with this green program. They give you a 10% coupon or a $10 off coupon or something. That gets you in the store or on their website. They figure you'll buy more. If you like it, you'll come back. So they have lots of reasons to participate and to basically provide these incentives. It's a rewards program. It's been unbelievably effective at increasing recycling rates in the places where they've done it. And other kinds of lotteries or other kinds of things where you basically, the reward someone gets is large enough for them to care about. You think they'll get it every time. There are lots of ways to do that. But the other point you raised about sort of the time scale of the signal, if what you want to do is, say, frequency regulation or ancillary services at the scale of really managing loads to respond to variation in intermittent generation, that actually is a case where it's not about just getting 10%, because if right now 80% of your generation is wind and the wind stops, you have a much more than a 10% problem, you got an 80% problem. So you either have to spin up other sources of generation or you got to shut those loads down, and that could happen very, very quickly. The latency of the communication networks is not a problem, honestly. I mean, we've done some experiments internally on exactly that, and we can we can get loads to match pretty much any load profile you want by cycling loads on or off a few times an hour across a large population of loads. And as long as you've got latency in terms of your communication with them that's in the sub a few second range, which is easy, it's just not an issue. And if that communication is unreliable and you can't talk to every load all the time, that's fine. You're talking to lots of them. So the aggregate effect is still what you need. So I think that the issue there is what percentage of the energy consumed can you control or dispatch, if you will, on that kind of time scale. Our estimate is it might be as much as a third or 30, 40%.
So just to build on this just quickly, the reason that up to a couple of seconds doesn't matter is because today the automated generation control that controls frequency and the like is every 4 seconds. So as long as you're operating within that time domain, you're okay. To give you a sense of the scale that Bill's talking about, the PJM market for capacity, when they went out for their latest auction for the forward 3 years, for the year 2012, I think it is 2012, 2013, I think it's 60% of the capacity that cleared the auction came from demand response. 60%. For energy, they now allow, in the last auction, they allowed energy conservation, energy efficiency to be bid in as an alternative to actually energy generated from a generation resource. And that, I think, cleared about just over 60% of the energy that would be provided in the forward years will be coming from these other resources. So these questions about how reliable these resources are going to be, given whatever price mechanisms, whatever behavioral dimensions, coming back to the reliability question that was talked about, if we're looking at 60% of both the capacity and the energy coming from end customer behavior, it's a very interesting question that needs to be, that is very relevant today.
Okay, and on that note, I think we're running out of time, so I'd like to thank the panelists very much, and we'll be around to answer questions.
For more, please visit us at stanford.edu.